Okay, cool. Hey everyone. So yeah, got some new instructors today. It's me and Ethan. I think I'm gonna be doing most of the talking, but maybe I'll let Ethan have a chance in a little bit. So we're starting on combinatorics today. It's kind of a weird branch of maths, I guess. It's hard to describe what it is exactly. I think a lot of the times it's kind of just described as like the branch of maths where like if it doesn't fit any of the other three, algebra, number theory, or geometry, um, it's the one that requires the least amount of theory, I think. So it's quite hard to teach. A lot of times you kind of just have to dive into some problems to like I guess just show some techniques and some heuristics. So that's most of what we're going to be doing today. We're just going to go over some problems. I guess I'll screen share the presentation slideshow. So this is what we're going to be going over today. We're probably going to be spending most of our time on the first topic here, counting, which is not counting on your fingers, like one, two, three. It's a different type of counting. We'll spend a little bit of time on binomial identities, although I feel like this isn't as important. And then thirdly, we're going to go over the pigeonhole principle, which is that one's pretty important. Okay, so our first topic is counting. So, so, so we're gonna okay. I'll first talk about like what counting is. It's kind of it's kind of hard to describe, but sometimes you're given some like let's say you're given some objects and you want to find a way of selecting objects or arranging objects given some certain criterion. Um, I don't really know how to explain it without examples, so I think that's what we're gonna do. We're just gonna go look at some examples. I'll give you guys a bit of time to try them out yourselves before we go over the answers. Oh, that was okay. We skipped example one. Okay, so here's the first example. So how many different 4-day holiday schedules can Mike make if he can choose between kayaking, hiking, or sailing for each day? So what I mean is, the first day he can either choose kayaking, hiking, or sailing. Then the next day, and the next day, and the next day, right? And so how many different schedules can he make? I'll give you guys maybe like 3 minutes just to try this out on your own. Oh yeah, feel free to I guess DM me on Zoom or I guess raise your hand maybe if you do think you have an answer. Actually, I don't know if raising the hand would be a good idea because I want to give everyone a chance to answer. Okay, sorry if you like if that was enough time for you to solve it, but since we are going to go through quite a few examples, I'm just gonna stop it here. I did receive a few answers, correct answers. That's nice. Um, since like okay, this is a relatively basic example, I'm not gonna like screen share my tablet and do any working. I'll just talk a little bit about it. So on the first day, he's obviously got three options. Um, and so from each of those three options, for the next day, he's got three more options, right? So, if he chose kayaking on the first day, then he's got three more options on the second day. So after the second day, he's got three times three or nine options. After the first 2 days, from each of these nine parts, again, there are three more parts. So you multiply by three again for the third day. And for the fourth day, you do the same. So at the end, there's three choices for the first day, three for the second, three for the third, three for the fourth. And multiplying them all together, you get three times three times three times three, which is 81. if anyone needs like further explanation on that, they could ask. But I'm just gonna move on from that one for now. So that one was I guess that was like probably one of the easier questions you would see in this kind of branch of maths. So here's our second example. Sally wants to shake everyone's hand at a 10-person meeting, but has to decide in which order to shake their hands. In how many ways can she shake everyone's hands? So I mean, like, yeah, how many different orders can she do it in? Yeah, I guess I'll give you guys another like 3 minutes to try this one. Okay, so I think yes. Sorry again if that was enough time, but um, I did again get a few answers. Some guys pretty quick with it. But I'll go over the answer now. Um, do you, I'm not sure if I want to just talk through this one or I think I might just talk through this one again. Sorry. Um, but the first so if we consider uh everyone at the meeting, there are 10 people. Obviously, Sally's not going to be shaking her own hand, so there are 9 people right now she could be shaking hands with. So we're just gonna consider the first person she shakes her hand with, and there's 9 people that could be the first person, right? Just one of the other 9 people at the meeting. So after she's shaken their hand, now she has to choose the second person to shake hands with, and since she's already, shaken one person's hand, there's only 8 people now that she can choose to shake hands with second. And if you keep going, there will be 7 people who she can shake hands with third, then six, then five, and all the way at the end, it's going to be just one last person because it's the last person she hasn't shaken hands with. So in total, it's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is somewhere I'm actually not sure. I'll probably use a calculator for this, not allowed in math and tests, but okay, just gonna do a little bit of cheating here. 362,880. So I hope you guys all understood that. Again, feel free to ask if you're a little unsure. Um, some people picked up on this, but there is a special function which does exactly what we just did, which is multiplying all the numbers up to a certain like integer. It's denoted with an exclamation mark and is pronounced n factorial. So it's just n times n minus one times n minus two all the way down to 2 times 1. So something like 5 factorial would just be 5 times 4 times 3 times 2 times 1, and so on. It's pretty useful whenever you're dealing with these types of counting questions, precisely because of questions like the last one we showed, right? So instead of having to write 9 times 8 times 7, whatever, you can just write 9 factorial, and that's a very concise way of just writing it. Okay, so let's go on to the next example. I think we have 5 examples in total. Okay, I might give a bit more time with this one. This one is I think this example is quite instructive. And I guess it kind of highlights a trap that you can maybe fall into in these types of problems. So yeah, I'll give you guys like maybe 5, 6 minutes to try this. Okay. It seems that there's I got answers from quite a few people. A lot of them were really good. Some of them were a little off. But I think some people fixed this as well. Um, I think I'll screen share my tablet just to do a bit of writing for this one. So if you just switch over. Wait, I don't know. Okay, sorry. Okay, so I guess the trap I was talking about is at first what you might try to do with this is right if we have our sorry, well, sorry, let me just minimize that. If we have our six letters, mind and Z, we might try to reorder them into six spaces like such, right? So if we try the same method as we did for our previous example, we would have six letters for the first spot, five for the next, then four, three, two, and finally the remaining letter for six factorial. The issue here is that we have two n's, if you notice. So let's label these n's n1 and n2. Then one possible ordering might be something like, if we just choose a random ordering, like this, M N1 Z, N2 D, and I. And we'll count that as one arrangement of letters. But we would also count M N2 N1 D, I as a second arrangement. When in reality, these two are the same because if you take away the little subscript, if you take away the one and the two, they're both the same. They're M, N, Z, N, D, I, the same letters in the same order. So actually, we've counted this one case as two cases, and we've actually overcounted by a factor of two because every time any case we've counted, there's like a dual case where the N1 and the N2 are swapped, and we counted that as a different one. So we need to actually divide this by a number. The six factorial isn't right. We've counted it like twice. We've counted every case twice over. So we need to actually divide it by two. More precisely, we're dividing it by two factorial because there's two factorial ways of arranging the n1 and the n2. Um, I think do we have a bit of time? We have a little bit of time, so I'll go a bit more in depth. Like for example, if we had okay, this isn't a word, but if we put a third n into mind nz, so it becomes mind nzn, and then we asked, how many ways are there of rearranging these letters now? Well, again, the naive approach would just be saying, okay, it's 7 factorial. But now we know that for each case, there are 3 factorial ways in which the ends could be arranged. They could be like this: n1, n2, n3, n2, n1, n3, and say n3, n1, n2, 2, 1, 2, 1, 3, and sorry, I'm running out of room here, but you get the idea. Well, I did the same case twice. Sorry about that. Getting a bit lost here. 1, 3, and then yeah, sorry about that too. Okay, so clearly there's 3 factorial ways of, well, not okay, it's not, maybe it's not clear, but there are 3 factorial ways of arranging 1, 2, and 3, right? Because there's, using the same logic, there's 3 numbers in the first spot, 2 for the second, and then finally 1 for the last one, right? So in fact, we count these 6 cases. If I just fill in we count these six cases, which are the same case, obviously, right? M, N, Z, N, D, I, N, as we count this one case, sorry, as six cases. So we have to divide this by six. Um, but more precisely, what we're actually doing is we're dividing it by 3 factorial. And so this is something called overcounting, right? Because our initial rough estimate of 7 factorial, we overcounted by quite a bit, actually, by a factor of six. And so, okay, whenever you're doing these types of questions, you gotta make sure that like every case you're counting is actually distinct, so you're getting the correct answer. And if it's not, then just divide by whatever number to make it correct. So this normally happens when you have like objects that are indistinguishable. In this case, we have some ends that that are indistinguishable. They look the same, so you got to make sure that you're not overcounting it. Um, okay, I think okay. I'm gonna go back to the slides now, and we're gonna move on to the next example. Oh, sorry about that. Okay, suppose 8 runners compete in a sprinting contest. How many ways are there for the 3 medals, gold, silver, and bronze, to be allocated to the runners? Okay. Let's go with the answer now. I got some pretty good responses from some people. Okay, so again, we're gonna go back to the idea of considering the first element. So in this case, the first placer, right? So since there's eight runners, obviously, again, there's gonna be eight people who could get first place, right? Any of them could get first place. Um, and after we've decided that, let's look at who's gonna get, silver, second place. Well, one person already got gold, so again, there's gonna be seven people who can get silver, and then there's gonna be six people who get bronze. But unlike last time where we, went all the way down to one, this time we don't really care like about the ordering of the last five, right? Like okay, I'm sorry guys, you guys are losers, right? You didn't win anything. Um, so now we just if we only care about the first three, we're just gonna look at 8 times 7 times 6. Eight for the first place, seven for the second place, and then um sorry, six for the third place. And actually, this is like it's 8 factorial divided by five factorial. Because if you imagine, listing out 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, over 5 times 4 times 3 times 2 times 1, like the tail of the 8 factorial, like the 5 times 4 times 3 times 2 times 1 is going to cancel out with the 5 factorial. You're going to be left with 8 times 7 times 6. So in general, if if you're like choosing three people from a group of eight, or choosing k people from a group of n and ordering them in some way, it will just be uh n factorial divided by n minus k factorial. And okay, if you don't necessarily understand that, that's okay, because a lot of these questions, the good thing about combinatorics is you can work through them pretty intuitively, right? If you're just going through the steps like I just did right now, how many people are there for the first, how many people could get the first place, how many people could get second place, how many people could get third place, and then that's the answer. So that's kind of the good thing about combi. You can just intuitively go through and get the answers. You don't need to really memorize too many formulas, even though formulas can help sometimes. Okay, so next I'm gonna be talking about this thing. I mean, I'm calling it a choose function. I don't think that's technically the correct name. I think the name of this thing is like a binomial coefficient. But okay, you don't need to know what that is, right? Basically it looks like this. You have two, like pretty big brackets, an n at the top, a k at the bottom. And what this function represents is it's oh, okay. Wait, sorry, Tara. The last one, sorry, it's sorry if I was a bit confusing in what I was saying. It should have been 8 times 7 times 6 because there's eight choices for the first place, seven choices for the second place, and then there's third choices. Sorry, six choices for the third place. Uh, yeah, sorry. That's really all you need to know. It's just 8 times 7 times 6. Okay, so this function represents the number of ways of choosing k items from a set of n different items. So, for example, if I have, like seven balls, like seven distinct balls, right? Like I can tell them apart. They're labeled 1 to 7, and I want to, say how many ways are there of choosing two of them? Well, it will be seven on the top and then two on the bottom, and you put these brackets around them, and then that's the numerical value, right? And here we have the formula. Um, yeah, I don't think I'll go over the proof of this, and I mean, okay, yeah. So there should be like a linked handout. I think that was emailed to you guys. You can look in there for the proof of this. I guess. I don't think I'll go over this lesson. So okay, unfortunately, this is something you're gonna have to memorize, right? Okay, it's kind of ironic. I just advertised Combi as something that doesn't need much memorization, but yeah, this is a very very useful, highly useful formula. So just for example, like if there were if there were three objects, like let's say A, B, C, and I wanted to choose two of them, right? Try using this formula and see what number you get. You can message me the number. Actually, okay, I'm not gonna, give you guys too much time just because we do have an exercise coming up, which is basically the same as what I'm doing right now. But yeah. So since we have, it would be three choose two. You plug in n equals three, k equals two into the formula, and what you should get is you should get the answer of three. And this makes sense, right? If you think about it, because if you have, let's say, three objects, A, B, C, I mean, you're choosing two of them. You can either choose A, B, A and B. You can choose A and C, or you can choose B and C. And I think it's pretty clear those are the only like sets of two objects you can choose. And notice here that choosing A and B is the same as choosing B and A. Order doesn't matter. You're just picking two objects out of these three objects. So yeah, intuitively the answer should be three, right? And it's good that the formula backs this up. Um, Actually, for example 5A, this is kind of like what I just asked you to do, but I guess with some larger numbers. Um, so yeah, okay, okay, yeah, you guys can use a calculator for this if you want. Okay, look, I'm not gonna sit here and make you guys do some tedious calculations. Okay, I'll just quickly go over A real quick. So okay, it's since we're selecting four people from a family of eight, that's just selecting eight items from a group of eight, right? So it's gonna be eight choose four, and if you just put in those numbers, n equals eight, k equals four into the formula, you should get the answer of 70, which I saw some people did get. Um, I think yeah, part B is definitely the more interesting question, so I'll give you guys quite a little bit of time to try doing that one. I'll give a little bit of a hint for part B. Sometimes instead of like figuring out the number of like possibilities that do work, it's easier to find out the possibilities that don't work or don't satisfy the conditions, and subtracting that from the total number of possibilities. Okay. Um, I think okay. I think I'll go with the answer now. Um, okay. I'll probably just go back to my tablet now. Okay. So so every possibility, right, either satisfies the condition or doesn't. So the total number of possibilities that do satisfy the condition and the total number of possibilities that don't satisfy the condition should equal the total number of possibilities. And here the condition is that the two twins are not in the photo together, right? Because that's what we want. That's what we want to be satisfied. We don't want the twins together in the photo. So using this, we see that if we just rearrange it a bit, we see that I mean, if we move this to the other side, to get the number of possibilities that do satisfy the condition, we need the total number of possibilities and the possibilities that don't satisfy the conditions. Okay, so what's the total number of possibilities? Well, the total number of possibilities is just every possibility where we're choosing four people from a group of eight, right? Which we figured out in the previous example. Wait, did I even say what the answer to the previous example was? I think I did. Okay, anyway, it's 70, right? So the total number of possibilities, this one right here, that should be 70. So now we should find the number of possibilities that don't satisfy the conditions. And what this would, what this would correspond to in our problem is like every single case where the two twins are together in the photo. So we want to find like how many ways like are there of choosing four people from this group of eight, such that the twins are in there. So obviously, if the twins are in there, we're gonna need to first of all choose the twins, right? So we kind of lock them in. Okay, we've already chosen two people. Okay, well we need to choose four people in total. So right, so we need to choose four people in total. So here's twin one, we've chosen them, and then here's twin two, we've chosen them. Now we need to choose two more people. Well, originally there were eight people in this pool, right? Three, four, five, six, seven, eight. Here are the eight people we could have chosen. But now we've chosen the two twins. There are only six people left in the pool to choose from. So how many ways are there of choosing two people from a group of six? I mean, that should just be six choose two, which is using the formula 6 factorial over 2 factorial times 6 minus 2 factorial, which is 720 over 1 mean second, which is equal to 15. Yeah, so there's 15 ways of choosing four people such that the two twins are together. Okay, but now we have our formula, right? Possibilities that satisfy the condition is the total number of possibilities minus possibilities that don't satisfy the condition. So that is just 70 minus 15, which is 55, and that's the final answer right there. So this is quite like a common, well, not maybe not common, but it's quite a useful method at least. Sometimes, like it's a lot easier to find the possibilities that don't satisfy the conditions. So if you're getting kind of a weird condition, try to look at like the opposite of that condition and see if you can get information from that. So that's just something to keep in mind. Okay, we're running a bit low on time now. Whoops. Okay, I'm gonna try get through binomial identities, you know, a little quickly, just because I don't think that's as relevant. Okay. and then we're gonna maybe spend one more time on pigeonhole. Okay, so a binomial identity, what is that? Uh, well, that is just, I mean, it's basically just like a fact. It's just something that always holds. It's something that's true, and obviously that's gonna be useful because you want things that are true, right? If something's always true, then you can use it like whenever you want. Okay, so the first thing we're gonna talk about is the symmetry of the binomial coefficient, which is with all like the choose function, right? Show that n choose k equals n choose n minus k. Um, okay, I won't give you guys time to solve this question because first of all, we're running a little bit on time. Okay, I'll just say that if you just plug this into the formula, you're gonna get like you're gonna show they're equal, right? But I'll talk about the combinatorial way, which is I guess a more intuitive way of showing it's true. So imagine you have n objects and you want to choose k of them to form a group, right? Well, how could you do that? Okay, first of all, you could just choose k objects from these n objects, right? That's pretty obvious. But a second like equally viable method is choosing objects to not be in the group. So you choose n minus k objects to not be in the group, and you take the remaining ones and put them in the group, right? So in that way, choosing k objects is the same as choosing nk objects to not choose. If that makes any sense, I think it does, right? Because you're always going to be splitting it into groups of a group of k and a group of n minus k. So choosing a group of k is the same as choosing a group of n minus k. Um, so that one was actually probably that one was definitely very useful, right? Just something to keep in mind, something to remember when you're dealing with binomial coefficient. And next thing we're going to be looking at is maybe the binomial theorem. Maybe you've heard of it. Okay, don't worry if you don't know what this stuff means, right? This funny looking thing is a sigma notation. It basically means yeah, like it means first of all plug in k equals 0 into this expression, and then plug in k equals 1, then k equals 2, all the way up to k equals n, and then you're gonna add them all together. Um, I'll expand it on my iPad just to show you guys like if you don't know what that means. So the question here is find the fifth term of the expansion of x plus 1 to the 12 and ascending powers of x. Okay, well, okay, this question isn't gonna like come up in Olympiad, right? But I guess I'm just using this as an example of how the binomial theorem of yeah, how the binomial formula actually would work. Okay, so it was what the hell is it? So wait, it was fifth term and okay, remember we're using ascending powers of x, so we're gonna start from the lowest power of x and move to the highest. So it'll be one plus. So we know that this is gonna look something like one plus something x plus something x squared plus something x cubed plus something x4, and then it's gonna keep going on. So we want that term right there because that'll be the first term. So using the theorem, it looks something like this. I think okay, the one I put up did x to the n minus k times y to the k. It doesn't really matter. You could just do x to the k times y to the n minus k, and the reason it doesn't matter is because, as we mentioned previously, the n choose k function is symmetric. Um, I'll just use this one though because that's the one I put up. So what this is actually saying is it looks something like n choose 0. So if you plug in k equals 0, you get this. Then if you plug in n equals 1, you get something like this. And then you just keep going like this, where you plug in k equals 0, you sum it, you plug in k equals 1, you sum it, and then you keep going all the way until you get to n. Okay, so clearly in our case, in our problem, we have y is equal to 1. So we're going to be using y is equal to 1 and n equals to 12. And if we just plug this in, we get plus 1 to the k. But clearly 1 to the anything is always just going to be 1, so we can kind of so that's going to be multiplied, not times. And anything multiplied by 1 is going to remain the same, so we can kind of just get rid of that. And if we just plug in k equals 0, we get 12 choose 0 times x to the 12 plus 12 choose 1 times x to the 11 plus 12 choose 2 x to the 10 and so on, right? But we want the term with x raised to the fourth power. So how do we get x raised to the fourth power? Well, we see that each term here, x is raised to the power of n minus k. So we want n minus k to equal 4 to get the fourth term, to get the power where we have x raised to the fourth power. Okay, so n minus k equals 4. That's going to be, oh shoot, sorry guys. It should be 12 minus k here just because it is, we're using n equals 12. So if 12 minus k is equal to 4, we therefore get that k is equal to 8. So we get that the term is the one where k is equal to 8. That's not right. I'm 4. So we want, so this is the term we're after, right? And okay, 12 choose, like, okay, I'm using my calculator for this. Then this is 495x to the 4. Okay, so that's yeah, that's how the binomial form is gonna work. Although I wouldn't say that one is hugely important, but actually I think that was more useful for school, like say like curriculum maths. Okay, so we have 10 minutes left to talk about pigeonhole principle. We might go a little bit over time. Actually, maybe not. I think Ethan, you there?
Oh yeah, hello.
Yeah, I think I might let Ethan take over now. Give him a bit of time to speak.
Oh wait, this is a bit sudden.
Oh yeah, I'm saying, but yeah, keep going. He got this.
The pigeonhole principle is basically to do with pigeonholes and pigeons. Well, what a surprise. Okay, so the basic concept of the pigeonhole principle, right? Let's say you have some number of like pigeonholes, right? And you have, let's say you have like 10 pigeonhole. Oh wait, 9 pigeonholes and 10 pigeons, right? The pigeonhole principle states that no matter how you put these pigeons inside the pigeonholes, you always end up with like one pigeonhole with at least 2 pigeons. And this theorem kind of seems weird, I guess, in the context of math because we don't deal with pigeonholes and pigeons. But when you get a question, you can kind of set up certain things to be pigeonholes and pigeons in order to solve the question. I mean, right now it might be hard to imagine, but we can like use some examples.
Yeah. So the theorem is if you put n plus one pigeons in n pigeonholes, at least one pigeonhole will have at least two pigeons if you don't cut up the pigeons in any way, right? And the proof of this, I think it's kind of obvious, but it's just basically like if you only put one pigeon in each pigeonhole, you're only gonna get n pigeons. So but you had n plus one pigeons. So where the hell is that last pigeon? Well, it must be in a pigeonhole, right? So that pigeonhole will have at least two. Okay. So this is a first example. I'll give you guys maybe like 5 minutes, 4 minutes to try this. Maybe only 3 minutes. But I don't know. Depending on how many like answers I get. Yeah, don't worry if you can't get this because obviously the first time you try and solve a question with pigeonhole, it is a bit weird trying to figure out like where the hell the pigeons are, where the pigeonholes are. So obviously we're just using this as an example to to show you guys. Okay, so I think I'll go over the answer now. Um, I'll go back to my tablet for this one. Okay, so conveniently we already have that n plus one, right? So those seem like pretty good candidates to be pigeons. I mean n plus one. We just need n pigeonholes now. So we're choosing n plus one numbers. Those are going to be our pigeons, and we're going to be putting them into n different pigeonholes. Okay, well we have two n like numbers in total, right? So it'll be nice to kind of partition them into groups of two, so that we have n pigeonholes in total. So what we're gonna do is we're gonna partition. So we have our numbers 1, 2, 3, 2n minus 1, 2n minus 2n, right? Those are our numbers. We're gonna partition them like this, right? 1 and 2, okay. 3 and 4, 5 and 6. So notice that there's two consecutive numbers in each of these pigeonholes. So on until we get to 2n minus 1 and 2n. And it's going to be, since it's an even number, 2n, we're going to get around like a whole number of pigeonholes. Okay, so here are n pigeonholes. And we chose we chose our numbers, right? We chose n plus 1 numbers. And each of those numbers belongs to at least one pigeonhole, right? Because these pigeonholes cover every number from every integer, sorry, from 1 to 2n. Okay, so by the pigeonhole principle, there must be at least two of our numbers which come from the same pigeonhole. Let's say 5 and 6. But that means that those two numbers are consecutive, which is what we wanted to show. We wanted to show that at least two of our numbers were consecutive. So yeah, that's yeah, okay, we're kind of running out of time, so that's all I'm gonna say on that. But yeah, that's an example of how to set up pigeonholes. So you want your pigeons to be like one or like one more than your pigeonholes, and which forces two of them to be in the same pigeonhole. Okay, so we have one last example to go through. Well, first we're gonna extend the pigeonhole a little bit. So instead of just n plus one pigeons, we're gonna have kn plus one pigeons placed in n pigeonholes. Then at least one pigeonhole will contain at least k plus one pigeons. So our earlier case was when we substituted in k equals one. But this works for any value of k. For example, if you have 17 pigeons in four pigeonholes, at least one of them will have five pigeons. And if you think about, okay, I'll go over why this is true, right? So if you just imagine there's only k, or at most k pigeons in each of these n pigeonholes, well, how many pigeons are you gonna have in total? You're gonna have k times n, right? Which is not enough to satisfy, like, to account for all the pigeons. There are k plus one pigeons. So clearly, you can't only have k pigeons in each pigeonhole. At least one of them must have k plus one. So we're gonna go over our last example here. 13 points are placed in a. Um, can you guys stay for another like let's say like 5 minutes? Is that okay, or do you guys like really need to go now? Okay, I'm gonna assume most of you guys can stay for let's say another 3 minutes. Sorry, okay, I'll be a bit. I'll give you guys a little less time for this then. 13 points are placed in a square with side at 2 centimeters. Show that there exist 4 points which form a quadrilateral with area less than or equal to 1 centimeter squared. Okay, nobody's messaged me yet. I'm not sure if that means no one's like got the answer yet, but I think I do think some people have left already, so I'm gonna just go over the I'm just gonna go over the answer now. Yeah, that's okay if you don't know how to do this one. These aren't meant, you're not meant to be able to solve these, right? These are examples for a reason. We have some exercises in the handout if you want to go try those on your own time. Um, so okay, I'll just go over to my tablet. And okay, so here I have the theorem k plus one pigeons and n pigeonholes implies there are k plus one pigeons in one pigeonhole. So in our case, we have our 13 points, which are our pigeons, and we gotta create some pigeonholes. Okay, so that's a bad square. Okay, that's our square here with area 4 centimeters squared. Okay, so we want we're gonna partition this in into four smaller squares, each with centimeter. So each of these has area of 1 centimeter squared, clearly, right? Since we partitioned 4 centimeter square into four like smaller squares, each of which is gonna have 4 divided by 4 equals 1 centimeter squared of area. So we have 13 points, which are our pigeons, and then we have four small squares. That's really bad handwriting, sorry. Which are our pigeonholes. So here we have, okay, we're gonna have k is equal to 3, n is equal to 4, which means that there must be at least 3 plus 1 or 4 pigeons in one of these pigeonholes. Um, and that okay, that makes sense, right? Because if you try to place only 3 in each pigeonhole, you're gonna come up short. You're gonna have 12 points, and that last point's gonna have to go somewhere. So there's gonna be 4 points in one of these squares. Let's just say it's the bottom right one. Why not, right? So we have 4 points somewhere around here, and we're gonna look at the area bounded by this quadrilateral, right? Okay, the area of this quadrilateral. I mean, since this quadrilateral is entirely contained within the square, the area of this quadrilateral must be less than or equal to the area of the square, right? But the area of the square, like I said, was 1 centimeter squared. So clearly the area of this quadrilateral is less than or equal to the area of the small square, which is equal to 1 centimeter squared, which shows that there does exist a quadrilateral which has area at most 1 centimeter squared. And yeah, so I think that's quite common in these shape type questions where you want to split the shape into smaller shapes, which are going to be your pigeonholes, and you can say something about how many points must be in one of those smaller shapes. Yeah, I think that's it. Something about like if you want you like ask for help, email. I guess wait, I'll throw my email real quick to everyone. If you want to send in some solutions, get a mark like you can send it here. Obviously, you could also just send it to the MINDNZ. Um, the MINDNZ account, give Nicole a bit more work instead of us. That'd be pretty cool as well. I'm gonna throw in Ethan's email. He can't slack off either. Yeah. I think you guys are free to leave now. Is anyone even still here? Oh, 9 participants. That's pretty cool.